A faint, all-pervasive static fills the entire cosmos. This is the cosmic X-ray background, a high-energy glow that has mystified astronomers for decades. It is not just empty noise, but a secret signal hiding the universe's most explosive and hidden events. By the end of this journey, you will understand 25 of its deepest mysteries, from the feeding frenzies of invisible black holes to the possible decay of dark matter itself. What could be producing this universal fog of radiation, and why does so much of it remain completely unexplained? What do you believe is the most profound secret the universe is keeping from us? The very first mystery is also the most fundamental. What is the source of this cosmic static? Decades ago, when the earliest X-ray satellites first scanned the heavens, scientists expected to see a dark sky punctuated by brilliant points of light from known objects like neutron stars or the hot gas within galaxy clusters. Instead, their instruments registered something far more puzzling, a faint, uniform fog of X-rays coming from every direction. This was the cosmic X-ray background, and its discovery completely rewrote our understanding of the universe's energy output. It meant that space was not mostly empty and dark at these high energies, but was instead filled with a pervasive, unseen glow. The initial challenge was simple yet profound. We could detect the fog, but we could not identify all the light bulbs creating it. Some of the glow was resolved over time into individual sources, like the searing accretion disks of supermassive black holes at the hearts of distant galaxies. But even after accounting for these known monsters, a significant portion of the background remained stubbornly unexplained. This unresolved portion is the true heart of the mystery. It points to vast populations of incredibly faint, distant objects that are simply too dim for our current telescopes to see individually. These could be trillions of hidden black holes, or perhaps entirely new types of astrophysical processes we have not yet even dreamed of. All sky maps from missions like ROSAT and the newer EROSIT reveal this glow in stunning detail, showing a universe that is fundamentally alight with high-energy radiation. The map looks smooth, a uniform sheet of energy, but this uniformity is an illusion. It is the collective whisper of countless unseen cosmic events, a history of violence and power written in X-rays we are only just learning to read. This unresolved background forces us to ask, what incredible phenomena are we still missing? This universal fog of X-rays may be hiding the answer to another profound cosmic puzzle, the case of the missing matter. Cosmologists have a very precise inventory of the universe's contents, and for decades they have known that a huge portion of the ordinary matter, the atoms that make up stars, planets, and you and me, is simply unaccounted for. This is the missing baryon problem. We know this matter must exist from our measurements of the early universe, but when we add up everything we can see in galaxies and gas clouds today, over half of it is gone. So where did it all go? The leading theory is that these missing atoms are not gathered in neat, visible structures, but are instead scattered throughout the vast, empty spaces between galaxies in the form of an incredibly hot, incredibly thin gas. Scientists call this the warm-hot intergalactic medium, or the WIM for short. Think of it like steam filling a massive cosmic kitchen. You cannot see the individual water molecules, but you know the steam is there because the air feels thick and humid. In the same way, this hot intergalactic gas is so diffuse that it is almost invisible, but it should leave a distinct fingerprint on the light that passes through it, particularly in the X-ray part of the spectrum. This is where the cosmic X-ray background becomes a crucial tool for detection. As the background radiation travels across billions of light years to reach our telescopes, it passes through these filaments of hot gas. The WIM should subtly absorb very specific wavelengths of X-rays, creating tiny, dark lines in the background spectrum, like a barcode that identifies the gas's composition and temperature. Finding these absorption lines is like searching for the faintest whisper of steam in a colossal, dark room. It requires incredibly sensitive instruments and a deep understanding of the X-ray light itself. If we can finally decode this cosmic barcode hidden within the pervasive static, we will not only solve the mystery of the missing baryons, but we will also complete our map of the universe's ordinary matter. This would confirm that the vast cosmic voids are not truly empty, but are instead woven through with a shimmering, hot web of atoms, a hidden architecture that holds the entire universe together. Deep within the heart of almost every galaxy, a sleeping giant lies in wait. These are the supermassive black holes, and when they awaken to feed, they become the most powerful sustained energy sources in the universe. We call these feeding frenzies active galactic nuclei, or AN. Their contribution forms a critical piece of the cosmic X-ray background puzzle. At the core of an AGN, a swirling disk of superheated gas and dust spirals into the black hole's gravitational clutches. This process releases a staggering flood of energy across the entire electromagnetic spectrum, from radio waves to the most energetic gamma rays. But it is in the X-ray band where these monsters truly reveal their power. The intense heat and magnetic fields near the event generate a searing blast of X-rays, a direct signature of matter being consumed on a cosmic scale. Yet for a long time we had a profoundly limited view of this population. Imagine trying to observe a brilliant lighthouse, but a thick, permanent fog blankets the coast. You know the light is there because you can see a faint, diffuse glow permeating the mist, but the source itself remains hidden. This is the phenomenon of obscuration. Vast donut-shaped clouds of gas and dust, known as toruses, encircle many of these active black holes. At optical or ultraviolet wavelengths, our view is completely blocked. We simply see a normal, quiet galaxy, but X-rays are different. They are so energetic that they can punch straight through those obscuring clouds, allowing our telescopes to see the brilliant, hidden engine within. This is why the cosmic X-ray background is such a vital map. It reveals the true, hidden population of these voracious black holes, ones that would otherwise be completely invisible to us. The unresolved glow we detect is, in large part, the collective X-ray scream of millions upon millions of these obscured AGN, their individual voices blended into a universal static by sheer distance. This leads to one of the most heated debates in modern astrophysics. With our most powerful X-ray observatories like Chandra and XMM Newton, we have been able to resolve a significant portion of the background into individual points of light, confirming they are indeed distant AGN. But the question remains, just how much of the glow have we explained? Is the entire background simply the sum of countless faint, obscured black holes, or is there a truly diffuse component that points to something else entirely, something more exotic and unknown? Every time we build a more sensitive telescope, we resolve a little more of the fog into individual stars, but the universe seems to hold a little back, preserving a core of mystery in the space between the lights. But even as we identify these hidden monsters, a deeper puzzle emerges from the shadows. The unresolved portion of the cosmic X-ray background is not a uniform smear of energy. It has a distinct character, a specific fingerprint that points directly to a hidden population of the most heavily obscured active galactic nuclei. These are not just veiled giants, they are the cosmic recluse, buried under such thick layers of gas and dust that even their powerful X-rays are partially smothered. At lower X-ray energies, their signals are almost completely absorbed, but at higher, more penetrating energies, they begin to leak through. This creates a distinct spectral signature, a telltale bump in the background's energy distribution that acts like a secret handshake, revealing their presence without showing their face. Finding them requires a cosmic multi-sensory approach. Deep X-ray surveys, like those from the Chandra and XMM Newton observatories, act as a first pass, detecting the faint, high-energy whispers that escape the obscuring cocoons. But to confirm their identity and understand their true nature, astronomers must combine this data with observations from other parts of the spectrum, particularly the infrared. The same thick dust that blocks X-rays absorbs the intense light from the black hole's accretion disk, heats up, and re-radiates that energy as a powerful infrared glow. It is like locating a hidden furnace by feeling the heat radiating from a closed door. By cross-matching the faint, hard X-ray sources with bright infrared objects, we can pull these hidden monsters one by one out of the cosmic static. Understanding this hidden population is not just an accounting exercise, it is crucial to modeling the life story of galaxies. We now believe that virtually every large galaxy went through an active phase, a period of violent growth and feedback driven by its central black hole. The obscured AGN we detect in the X-ray background represent a critical, hidden chapter in this story, a phase when the black hole is actively feeding but its growth is shrouded from view. Pinpointing their exact numbers and the total energy they contribute to the cosmic fog remains one of the greatest challenges in X-ray astronomy. Every new survey reveals more of them, but the fainter and more distant they are, the harder they are to separate from the background noise. How many of these veiled giants are truly out there, and did their hidden feast shape the galaxies we see today? The answer is written in the faint, high-energy static waiting to be decoded. While supermassive black holes command attention with their cosmic fury, a quieter, more pervasive source of X-rays has been shining in our own backyard all along. Every star like our Sun possesses a seething outer atmosphere, a crown of fire known as the corona. Heated to millions of degrees by tangled magnetic fields, these coronae constantly emit a faint whisper of X-rays. Our own Sun's corona is a familiar example, its soft X-ray glow intensifying during the violent storms of solar flares. Now expand that single, local phenomenon across the universe. Multiply it by the hundreds of billions of stars in a single galaxy, and then again by the trillions of galaxies scattered across the cosmos. This raises a fascinating and complex question. Does the combined X-ray hum from all the ordinary stars in the universe add up to a significant portion of the cosmic static, particularly at the lower or softer X-ray energies? The answer is far from simple. Calculating this stellar contribution is a monumental task, an exercise in cosmic demographics. It requires a deep understanding of how stars of every possible type, mass, and age behave in X-ray light. A young, rapidly spinning red dwarf star can be thousands of times more X-ray luminous than our middle-aged sun, while a massive, elderly giant might produce almost none. The X-ray output of a star depends on its magnetic activity, which in turn is influenced by its rotation, its composition, and even its location within a galaxy. Stars crowded in dense galactic cores might behave differently from those in the quiet outskirts. To build a reliable model, astronomers must essentially take a census of stellar X-ray activity across the entire universe, a task that pushes the limits of our observational capabilities. We can observe the brightest stellar X-ray sources in nearby galaxies, but the faint, collective glow from all the ordinary stars in a distant galaxy blends into an unresolved fog, indistinguishable from other, more exotic sources. So the mystery persists. Is the soft X-ray background in part a cosmic chorus of countless trillions of singing stars? Or is their collective voice merely a faint whisper against the roar of hidden black holes and hot intergalactic gas? Determining the true weight of this stellar symphony is crucial, for until we know how much of the background comes from these familiar sources, we cannot be certain how much is left for the truly unknown. Beyond the realm of individual galaxies and hidden black holes lie the true titans of the cosmos, galaxy clusters. These are the largest structures in the universe held together by gravity, immense cities of 1,000 galaxies or more. But the galaxies themselves are merely the visible stars in this metropolis. The true bulk of a cluster is an enormous, diffuse cloud of superheated gas known as the intracluster medium. This gas is heated to temperatures of tens of millions of degrees, so hot that it does not shine in visible light, but instead glows with an intense, pervasive X-ray radiance. This presents us with a direct and compelling mystery. If a single galaxy cluster can be such a brilliant X-ray beacon, what is the combined effect of every cluster in every direction across the entire history of the universe? How much of the cosmic X-ray background is simply the accumulated light from these colossal structures? The answer is surprisingly difficult to pin down. We can easily observe and measure the powerful glow from nearby massive clusters, but as we look deeper into space and further back in time, we encounter younger, smaller, and fainter clusters and groups of galaxies. Their individual X-ray emissions are incredibly weak, blending seamlessly into the universal static. It is like trying to hear the individual hum of every single air conditioner in a vast, sprawling city from miles away. The combined noise creates a pervasive drone, but picking out any single unit becomes impossible. This unresolved hum from distant clusters and groups is a critical piece of the background puzzle. Pinpointing its exact contribution would tell us a great deal about the growth of cosmic structure itself, revealing how these giant assemblies of matter evolved over billions of years. But the enigma deepens further. Is this hot gas confined only to the dense hearts of these clusters, or does it extend out into the even more tenuous filaments of the cosmic web that connect them? Theory suggests there should be a faint, diffuse X-ray glow from the gas in these intercluster bridges, the very same warm, hot intergalactic medium we suspect holds the missing matter. Detecting this whisper-thin emission against the already faint background is one of the ultimate challenges in X-ray astronomy. It would be like trying to see the faint, glowing mist between mountain peaks on a foggy night. If we can finally measure it, we will not only solve a part of the X-ray background mystery, but we will also have a direct map of the hidden skeleton of the universe, the vast, hot architecture upon which everything is built. Beyond the brilliant beacons of massive galaxy clusters lies a far more numerous yet invisible population. These are the faint, undiscovered galaxy groups, the cosmic equivalent of small towns and villages scattered across the vast countryside. While a massive cluster might contain thousands of galaxies, a group may only have a few dozen, all bound together by a much weaker gravitational pull. Their diffuse halos of hot gas are correspondingly fainter, cooler, and far more difficult to detect. Yet, these unassuming groups could be the missing link in our understanding of the X-ray background. Think of the cosmic web as a colossal map of lights. The big cities, the massive clusters, shine brightly and are easy to spot. But the true structure of the land, the connecting roads and countless small settlements, remains shrouded in darkness. These faint galaxy groups represent that hidden infrastructure. They are so numerous across the universe that their combined, whisper-thin X-ray glow could add up to a surprisingly large portion of the unresolved cosmic static. We are essentially missing an entire demographic of the universe in our X-ray sensors. The challenge in observing them is immense. Their signal is not just weak, it is entangled. The soft X-ray glow from the hot gas in a distant group is easily confused with the combined light from individual stars within its galaxies, or even with the faint emission from the warm, hot intergalactic medium that might surround it. It is like trying to hear the specific hum of a single, distant power line when you are already surrounded by the low drone of an entire city. Our current telescopes simply do not have the sensitivity to cleanly separate one faint, diffuse source from another at such vast distances. This is why they remain a theoretical ghost in the machine, a predicted component of the background that has so far eluded direct confirmation. Their discovery, however, would revolutionize our picture of cosmic evolution. These groups are likely the building blocks that eventually merge to form the massive clusters we see today. Studying their hot gas would reveal the conditions under which galaxies first began to assemble into larger structures. The next generation of X-ray observatories with vastly improved sensitivity and resolution are being designed for this very hunt. They will act like cosmic hearing aids, allowing us to filter out the noise and finally listen for the faint, collective hum of this hidden universe. Finding this missing population would not only solve a major part of the X-ray background mystery, but it would also illuminate the darkest, most common pathways of galactic growth. Beyond the hot gas of galaxy clusters and the whispers of hidden black holes lies a possibility so profound it redefines the nature of reality itself. What if a portion of the cosmic X-ray background is not coming from any known type of matter at all, but from the ghostly decay of dark matter? This is one of the most speculative and thrilling frontiers in all of modern cosmology. We know dark matter exists because its gravitational pull guides the motion of galaxies and sculpts the cosmic web, yet it has never been directly seen. It does not emit, absorb, or reflect light, making it utterly invisible to our telescopes. But what if, just maybe, it is not completely stable? Certain theoretical models propose that dark matter could be made of exotic particles that very slowly decay into something else. One leading candidate is a hypothetical particle known as a sterile neutrino. If these particles exist, their decay could produce a faint, specific signal, a single, sharp spike of X-ray light at a very precise energy. This would be the smoking gun, the first direct evidence of dark matter's true nature. The hunt for this signal has focused intensely on a tiny, mysterious bump in the X-ray spectrum at an energy of around 3.5 kilo-electron-volts. This faint emission line has been tentatively detected by several X-ray observatories, including XMM Newton and Chandra, appearing in the stacked data from galaxy clusters and even in the Andromeda galaxy. The excitement is palpable, for this line has no obvious, mundane explanation. Known atomic processes, the usual fingerprints of hot gas, do not produce a line at this specific energy. Could this be it? Could this be the long-sought whisper of dark matter decaying in the vast, empty spaces of the cosmos? Yet, the scientific community remains deeply divided. Skeptics argue that the line could still be produced by more ordinary, if poorly understood, atomic physics, perhaps from swirling clouds of hot sulfur ions. The signal is at the very edge of what our current instruments can detect, a faint ghost in the data that is incredibly difficult to confirm or refute. The race is now on to solve this mystery. New missions are being planned with the specific goal of studying this 3.5 kV line with unprecedented precision. If it is confirmed to be dark matter decay, it would mean that the cosmic X-ray background, this universal fog we have been studying, contains within it the dying breath of the universe's most mysterious substance. We would be listening to the final, faint sigh of particles that have shaped the cosmos since its very beginning. Is the universe's static hum partly a ghostly chorus, a signal from the dark side itself? This faint, ghostly line at 3.5 kilo-electron-volts has become one of the most contentious puzzles in modern astrophysics. Its story begins not with a single, clear shout, but with a persistent, quiet whisper that emerged when scientists stacked the X-ray data from multiple galaxy clusters. By combining observations of these massive objects, astronomers could amplify the faintest signals, and that is when they saw it, a tiny, unexpected bump in the spectrum that refused to go away. The initial detections, primarily from the XMM Newton Observatory, sent ripples of excitement through the community. The line appeared where no known atomic transition should be. It was as if you were listening to a symphony and heard a single, pure note from an instrument that did not exist. The most tantalizing possibility was immediately clear. This could be the signature of a sterile neutrino, a hypothetical dark matter particle decaying into an ordinary photon. The implications of such a discovery are almost beyond comprehension. It would be the first direct detection of a dark matter particle, confirming its identity after decades of knowing it only by its gravitational shadow. It would open a direct window into the invisible 85% of the universe's matter, revolutionizing both particle physics and cosmology in a single stroke. The entire cosmic X-ray background would suddenly be seen in a new light, its faint static containing the death rattle of the universe's most dominant substance. But extraordinary claims require extraordinary evidence, and the scientific process immediately swung into action to test this breathtaking idea. The hunt for confirmation turned to other places where dark matter should be densely concentrated, like the center of our own Milky Way galaxy. If the line were truly from dark matter decay, it should be strongest there. Some groups reported seeing the same spectral bump in that data, while others saw nothing but noise. The controversy only deepened. The painstaking work of elimination began. Could this line be produced by something more ordinary, something we simply had not accounted for properly? The prime suspects became familiar elements like potassium and argon. When these atoms are stripped of their electrons in searingly hot plasma, they can emit X-rays at very specific energies. The problem is that the 3.5 keV line sits perilously close to where multiple, overlapping lines from these elements could create a blended signal that mimics a single new line. It is the ultimate cosmic case of mistaken identity. Disentangling this requires not just powerful telescopes, but a deep, precise understanding of the complex physics of hot, swirling gas in galaxy clusters, including its temperature, density, and chemical composition. Failed attempts to confirm the line have poured cold water on the initial excitement, but they have not killed the mystery. Each non-detection forces a refinement of the models, pushing us to ask if we are looking in the right way, or if the signal is even fainter and more elusive than we first believed. The 3.5 keV line remains in a state of quantum uncertainty, both there and not there, a phantom in the data that continues to haunt the edges of our knowledge, daring us to prove its existence or finally lay it to rest. That faint, ghostly line is not the only spectral surprise hiding in the cosmic static. As we shift our focus to the lower energy or soft part of the X-ray background, we encounter another profound puzzle, an unexplained surplus of emission known simply as the soft X-ray excess. It is as if the universe has turned up the brightness on a specific color of its high-energy palette, and no one knows why. This excess is a glow that seems to be more than the sum of all the known contributors, like distant active galactic nuclei and the hot gas within galaxy clusters at these softer energies. The central challenge in solving this mystery is a problem of cosmic perspective. A significant portion of this soft X-ray glow might not be cosmological at all, but could originate much closer to home from within the halo of our own Milky Way galaxy. Imagine our galaxy is surrounded by a vast, invisible atmosphere of incredibly hot gas, a corona of its own. This gas, heated to temperatures of millions of degrees by supernova explosions or by matter falling into the galaxy, would naturally emit a diffuse fog of soft X-rays. From our vantage point inside the galaxy, we are essentially sitting inside the very fog we are trying to see through. This creates an immense challenge for astronomers, akin to trying to study the faint, distant light of mountains on the horizon while you are standing in the middle of a city shrouded in its own brightly glowing mist. Every observation of the distant cosmic X-ray background must first be carefully cleaned, with this potential local emission subtracted out. But how do you accurately measure and remove a glow that you are embedded within? It is a delicate, painstaking process, and any error can leave behind a false signal that looks like a cosmic mystery but is really just a local ghost. This leads to a fierce debate. Is the soft X-ray excess truly a cosmological phenomenon, a real feature of the distant universe, or is it merely an artifact, the leftover glow from our own galactic backyard that we have not perfectly erased? The answer could reshape our understanding of the cosmos. If the excess is truly cosmological, it points to a vast, previously undetected reservoir of warm, hot intergalactic gas, the very medium thought to hold the universe's missing atoms. It could be the signature of the cosmic web itself, a faint, pervasive glow from the filaments that connect all galaxies. Or it could signal an entirely new class of faint, soft X-ray sources that our current telescopes cannot resolve. The mystery of the soft X-ray excess forces us to look both inward and outward, to question what is local and what is universal, reminding us that sometimes the greatest cosmic secrets are hidden in the fog right outside our door. Our own galactic neighborhood holds a key to this puzzle, a vast and invisible atmosphere of searing gas that envelops the entire Milky Way. This is the galactic halo, a spherical cloud of million-degree plasma that may be the source of a significant portion of the soft X-ray background we observe. The evidence for this local fog comes from a clever cosmic trick known as a shadowing experiment. Astronomers search for dense, cold clouds of neutral hydrogen gas drifting within the galactic halo. These clouds are so thick and cold that they are completely opaque to distant X-rays, acting like cosmic blackout curtains. When we point our X-ray telescopes at such a cloud, we should see a dark patch in the background glow, an absence of the distant cosmological signal. But that is not what we see at all. Instead, we often detect a faint, uniform X-ray glow coming from the cloud itself. This can only mean one thing. The X-ray source is not behind the cloud, but in front of it, located between the cloud and our telescopes. We are seeing the soft X-rays emitted by the hot gas of our own galaxy's halo, with a dark cloud silhouetted against it. This local origin creates a profound complication, forcing us to ask how much of the soft X-ray background is truly from the distant universe and how much is just the glowing fog in our own backyard. The very existence of this hot halo raises another fundamental question about its nature. Is this corona a static, fossilized relic, a leftover from the Milky Way's violent birth billions of years ago, when vast clouds of primordial gas collapsed to form our galaxy? Or is it a dynamic, living structure constantly being replenished and reheated by ongoing cosmic weather? The leading theory points to a continuous cycle of violence. Supernova explosions throughout the galactic disk blast titanic winds of hot gas, driving it outwards to inflate and sustain the halo. At the same time, our galaxy is continually accreting matter, drawing in cooler gas from intergalactic space. As this gas falls in, it can be shock-heated to extreme temperatures upon impact with the existing halo, adding more fuel to the fire. Determining which process dominates is crucial. A fossil halo would tell a story about our galaxy's ancient past, while an actively heated one reveals a system still in turbulent flux, breathing in and out on a galactic scale. Unraveling this mystery is essential for cleaning our view of the distant cosmos, for we must first see through our own glowing window before we can truly perceive the universe beyond. But the galactic halo is not the only local fog clouding our view. We are also floating inside a much smaller but equally important cavity of hot gas known as the local hot bubble. This is a region of incredibly thin, million-degree plasma that envelops our entire solar system, extending outwards for roughly 300 light-years in most directions. We are living inside a cosmic soap bubble, one that glows faintly with soft X-rays. Its origin story is written in violence. Astronomers believe that a series of supernova, massive stars that exploded in our galactic neighborhood over the last 10 to 20 million years, detonated with enough force to carve out this vast cavity in the surrounding interstellar medium. These stellar cataclysms swept up the cooler gas and dust, pushing it outwards to form the bubble's dense shell, while simultaneously filling the interior with a scorching, diffuse plasma. This hot, thin gas is what produces the soft X-ray glow that we see in every direction, a permanent, local fog that our telescopes must peer through. The central mystery of the local hot bubble is one of structure and influence. Precisely mapping its true extent and density is incredibly difficult because we are inside it. Its shape is not a perfect sphere, but a complex, lumpy structure with tendrils of hot gas extending in some directions and perhaps even tunnels connecting it to other nearby cavities. How much of the soft X-ray background that we meticulously measure is actually produced by this local furnace, and how much is genuinely from the distant cosmos? The answer is critical, for if we overestimate the bubble's contribution, we might erase a real cosmological signal, dismissing a whisper from the warm, hot intergalactic medium as mere local noise. Conversely, if we underestimate it, we could be fooled into chasing cosmic phantoms, mistaking the glow from our own celestial backyard for a profound discovery about the universe at large. Untangling this local signal from the global background is a monumental task in cosmic forensics, forcing us to understand the detailed history of our own stellar neighborhood before we can ever hope to see the universe clearly. The unresolved hard X-ray background is a far more stubborn mystery than its softer counterpart. This high-energy radiation represents the universe's most deeply buried secrets, a cosmic static that even our most powerful observatories struggle to break apart into distinct points of light. While the soft X-ray background could be influenced by local fog, the hard X-ray glow is almost certainly cosmological, emanating from the most violent and hidden events across the cosmos. Its very resistance to being resolved tells us that we are dealing with objects that are not just distant, but are purposefully cloaked. The leading suspects in this high-energy case are a specific class of active galactic nuclei known as Compton-thick AGN. Imagine a supermassive black hole at the heart of a galaxy, but instead of being surrounded by a mere donut of gas and dust, it is buried under a veritable fortress of material. This obscuring cloud is so incredibly dense, with a column of atoms so vast that it acts like a cosmic X-ray shield. Even the most penetrating hard X-rays struggle to escape. Most are absorbed, while others are scattered in a process called Compton scattering, which gives these objects their name. The tiny fraction of radiation that does leak out is incredibly faint, making these black holes nearly invisible ghosts in our telescopes. They are the ultimate cosmic recluses, feeding voraciously but emitting only a faint, high-energy whisper. Detecting them requires a multi-wavelength hunt. Since their direct X-ray signal is so suppressed, astronomers often find their infrared signature first. The same thick material that blocks the X-rays absorbs the black hole's intense light, heats up, and glows brightly in the infrared part of the spectrum. It is like finding a hidden furnace by the heat radiating from its brick walls. By combining deep infrared surveys with the most sensitive hard X-ray observations, we can finally pinpoint these invisible giants. Yet for every one we find, countless more are believed to remain hidden, their collective, muffled screams blending into the pervasive hard X-ray static. This unresolved background is the cumulative whisper of this hidden population, a constant reminder that for every brilliant quasar we see, there could be 10 heavily shrouded black holes lurking in the shadows, their growth hidden from view. But could there be something else contributing to this relentless high-energy fog? The extreme nature of the hard X-ray background leaves the door open for even more exotic explanations, phenomena that push the very boundaries of known physics. Finding these cosmic recluses demands a kind of astronomical detective work, relying on subtle clues rather than direct sightings. Since their primary X-ray light is almost completely smothered, astronomers have learned to search for the ghostly echoes they leave behind. When the intense radiation from the black hole's accretion disk slams into the surrounding fortress of dust and gas, it can be reflected or scattered back into space. This creates a faint secondary signal, a spectral signature of matter that never made it into the black hole but instead bounced off the obscuring walls. It is like hearing a faint whisper echo off a distant, unseen canyon wall, proving the canyon is there even if you cannot see it. One of the most crucial clues in this search is a specific fingerprint in the X-ray spectrum known as the iron K-alpha emission line. The incredibly hot material around the black hole floods the surrounding cloud with radiation, exciting the iron atoms within it and causing them to emit a very distinct spike of X-ray light at a precise energy. This bright, narrow line acts as a beacon in the fog, a direct indicator of dense, cold gas being illuminated by a hidden, powerful source. The strength and shape of this iron line tell a detailed story about the geometry and thickness of the obscuring material, allowing astronomers to confirm they have found a Compton-thick AGN even when its main glow is completely invisible. These elusive objects are far more than just a cosmic curiosity. They represent a fundamental, hidden chapter in the life story of supermassive black holes. We now believe that virtually every giant black hole goes through a heavily obscured phase, a period of rapid growth shrouded by the very material it is feeding upon. During this time, the black hole is actively building its mass, hidden from view by the cosmic dust of its own construction site. This makes them a vital piece of the puzzle, not just for the X-ray background, but for our understanding of how the most massive objects in the universe came to be. If a large population of these Compton-thick AGN exists, their collective muffled screams could easily account for the stubborn portion of the hard X-ray background that has resisted all attempts at resolution. Their discovery forces us to rewrite the cosmic ledger of black hole growth, suggesting that the most important phases of their lives are not the brilliant, visible quasars, but the quiet, hidden feasts happening in the dark. Just how many of these shadowy giants are we still missing, and what secrets about our universe's violent youth are they keeping? Amidst the grand tapestry of galaxies and hidden black holes, there exists a more intimate yet equally violent kind of cosmic partnership. These are X-ray binaries, systems where two stars are locked in a deadly gravitational dance. In these pairs, a normal star orbits a stellar corpse, a neutron star or a stellar mass black hole. The immense gravity of the dense corpse relentlessly strips material from its companion star. This stolen gas does not fall directly in, but spirals into a swirling, superheated disk, screaming out a torrent of X-rays as it plummets toward its final destiny. A single one of these systems can outshine the X-ray output of our entire sun by a factor of 1,000,000. Now, multiply that by the countless billions of binaries that must exist within a single galaxy, and then across the trillions of galaxies in the observable universe. Their combined, integrated emission forms a persistent, faint hum woven throughout the cosmic X-ray background. Quantifying this hum is a monumental challenge in cosmic accounting. It requires us to understand the life cycles of these violent pairs. There are two main types. High-mass X-ray binaries contain a massive, young star and are brilliant but short-lived, ending when the massive star explodes as a supernova. Low-mass X-ray binaries, however, are the true stealth contributors. Here, a neutron star or black hole slowly consumes a smaller, sun-like star. These systems can persist for billions of years, emitting a steady, faint trickle of X-rays that makes them incredibly difficult to detect at intergalactic distances. Their faint, persistent glow is like the combined light from all the nightlights in a sleeping city, seen from orbit. Individually, each light is Chinese letter, Chinese letter, Chinese letter, Chinese letter, but together they create a diffuse, pervasive illumination. This is the central mystery of their contribution. We can easily see the brilliant, flaring binaries in nearby galaxies, but the combined output of the vast, faint population of low-mass systems blends into an unresolved fog, indistinguishable from the light of obscured supermassive black holes or the hot gas of galaxy clusters. To model their true impact, astronomers must become stellar demographers, creating complex simulations that predict how many of these binaries form, how brightly they shine, and for how long. The answer depends on the history of star formation in a galaxy, its age, and its chemical composition. An old elliptical galaxy, for instance, should be filled with the faint, long-lasting glow of ancient low-mass X-ray binaries, the lingering embers of stellar partnerships formed eons ago. Their collective voice is a vital part of the cosmic static, a reminder that the universe's high-energy symphony is not just played by soloists, but by an immense, unseen choir of stellar cannibals. How much of the background's persistent whisper is, in fact, the sound of stars slowly consuming each other in the dark? Even the most brilliant quasars have countless dimmer cousins, and their sheer numbers create a statistical puzzle at the very edge of detection. Astronomers map this hidden population using a powerful tool called the luminosity function, a cosmic census that charts how many active galactic nuclei exist at every possible level of brightness, from the blazing beacons to the faintest embers. We have a good grasp of the bright end, but the behavior at the faint end remains one of the most critical unknowns in deciphering the X-ray background. The central question is deceptively simple. As we look at fainter and fainter black holes, does their number continue to grow, rising steadily into a vast, unseen multitude? Or does the curve eventually flatten out, suggesting a fundamental limit to how many of these dim monsters can exist? The answer to this statistical question holds the key to the entire puzzle. If the faint end of the luminosity function is steep, meaning the number of AGN rises dramatically as we go to lower luminosities, then the collective glow from this immense hidden population could account for nearly all of the unresolved X-ray background. The universe would be teeming with faint, obscured black holes, and the cosmic static would simply be the sum of their muffled voices. This would be a universe where our current inventory of cosmic engines is almost complete. But if the faint end is shallow, if the number of faint AGN does not increase as much as we predict, then we face a profound dilemma. A flat luminosity function would mean there are simply not enough faint, known-class black holes to explain the pervasive glow we observe. A significant portion of the background would remain unaccounted for, its origin pointing toward something else entirely. Perhaps an entirely new class of faint X-ray sources we have not yet imagined, or a more exotic process woven into the fabric of space itself. Resolving this is a monumental technical challenge. Peering into the faintest depths requires pushing our most powerful observatories to their absolute limits, conducting deep field surveys that stare at a single, seemingly empty patch of sky for days or even weeks. Each of these campaigns is a fishing expedition in the darkest cosmic waters, hoping to snag a few more of these elusive, faint points of light to add to the census. Every new data point helps refine the shape of the luminosity function, telling us whether we are closing in on a final answer or if the universe still has a major surprise in store. The faint end is not just a statistical abstraction, it is the frontier between a known universe and an unknown one, and we are only now beginning to map its shores. The faint X-ray static we observe is not a single, timeless photograph, but a layered movie of the universe's entire history. Each photon has been traveling for billions of years, and by measuring its energy and direction, we can rewind the cosmic tape. Deep X-ray surveys function as powerful time machines, staring at a single patch of sky for so long that they collect the faint whispers from the most distant, and therefore the youngest, regions of space. The mystery we now face is reconstructing the plot of this epic film from these fragmented, ancient snapshots. How has the cast of X-ray characters changed over the eons? The evidence points to a universe of dramatic and violent youth. When we look back to when the cosmos was just a few billion years old, we find that active galactic nuclei were far more common and ferocious than they are today. The universe was a brighter, more chaotic place, filled with brilliant quasars feasting on vast reservoirs of gas. This golden age of black hole activity seems to coincide with a period of intense star formation in galaxies, suggesting a profound and intimate connection. It is as if the galaxy and its central black hole grew up together, one fueling the other in a complex dance of construction and destruction. But piecing together the precise timeline of this relationship is incredibly difficult. Did the black holes fire up first, their intense radiation and powerful jets triggering the collapse of gas clouds to form new stars? Or did the starbursts come first, funneling vast amounts of fuel toward the galactic center and feeding the sleeping giants within? The X-ray background holds the integrated light from all these events, a blended record of this cosmic synergy. The unresolved portion of the glow is particularly crucial, as it likely contains the collective output of the faintest, most heavily obscured black holes from this critical era. These are the hidden construction sites of the early universe, where supermassive black holes were rapidly building their mass behind thick veils of dust. Understanding their evolution is key to solving the puzzle. Did they all turn on at once in a universal frenzy, or was it a more staggered, drawn-out process? The answers are written in the faint statistical patterns of the background radiation, a code we are only just beginning to crack. This temporal dimension transforms the mystery from a simple inventory into a dynamic story of growth, revealing that the universe's high-energy fog is the fading echo of its most tumultuous and formative years. This uniform cosmic static is not a perfect, featureless sheet. If you listen closely to its faint hiss, you can hear subtle imperfections, tiny statistical wrinkles in the fabric of the glow. These are the anisotropies of the X-ray background, minute fluctuations in its intensity from one point in the sky to another. They are not random noise, but a coded message about the hidden structure of the universe. Think of it like this: you are standing outside a vast, darkened stadium filled with a murmuring crowd. You cannot see a single person, but by carefully analyzing the rise and fall of the collective sound, you could learn a great deal. You could estimate the total number of people. You could tell if they were evenly spaced or clustered together in small, conversational groups. The specific character of the murmur holds secrets about the crowd itself. This is precisely what astronomers do with the X-ray background. By mapping its faint fluctuations with exquisite precision, they can perform a kind of cosmic statistics on the sources they cannot see directly. The pattern of these anisotropies acts as a powerful proxy. If the unresolved glow comes predominantly from a vast number of extremely faint, point-like sources, like countless hidden black holes, the fluctuation pattern will have a specific signature. It will look a certain way statistically. If, however, a significant portion comes from truly diffuse emission, like the faint glow from the warm, hot intergalactic medium, the pattern of the wrinkles will be different, smoother, and more spread out. It is a powerful, indirect way to probe the invisible. By measuring the angular scale of these fluctuations, scientists can even estimate the typical size and distance of the dominant unresolved sources, painting a picture of their distribution across cosmic history. This technique does not give us a beautiful, resolved image of individual objects, but it provides something equally valuable, a statistical census of the unseen. It tells us that the fog is not a fundamental property of empty space, but is indeed composed of countless tiny embers, each too faint to see on its own, but together creating a universal veil. What do these subtle wrinkles reveal about the true population of the cosmic dark? This same cosmic dust that hides black holes in X-rays also betrays their presence in another part of the spectrum. While our X-ray telescopes struggle to see through the fortress, our infrared observatories see the walls themselves glowing with absorbed heat. The universe's hidden monsters are painting a dual portrait, one in high-energy whispers and another in low-energy warmth. This leads us directly to a profound and related mystery, the cosmic infrared background. This is a pervasive, all-sky glow of infrared light, a faint heat signature that mirrors the X-ray static in its universality. The two backgrounds are deeply intertwined. The same population of heavily obscured active galactic nuclei that contribute to the hard X-ray background should be responsible for a significant portion of the infrared glow. The physics is beautifully straightforward. The thick dust and gas that shroud these black holes absorb the intense optical and ultraviolet light from the accretion disk. This dust doesn't just block the light, it heats up, often to temperatures of hundreds of degrees, and then re-radiates all that captured energy in the infrared. It is a cosmic conversion process, turning the brilliant, hidden light of a quasar into a diffuse, warm halo. The central mystery, then, is one of cosmic accounting. Do the numbers add up? If we take our best models of the hidden black hole population, based on the X-ray background, and calculate how much infrared light they should produce, does it perfectly match the infrared background we actually observe? Reconciling these two universal glows is one of the most critical tests for our entire understanding of how galaxies and their central black holes evolved together. A perfect match would be a triumph, confirming that we have correctly identified the hidden players and understood their energy output. But what if there is a discrepancy? A shortfall in the infrared background would suggest that our census of dusty AGN is incomplete, that there are even more of these shrouded giants than we thought, perhaps in a phase so deeply buried they emit almost no infrared light at all. Conversely, an excess of infrared light would point to other mysterious sources of cosmic warmth. It could imply a vast population of extremely dusty starburst galaxies, where stars are forming at a ferocious rate, their light completely converted to infrared by enclosing dust clouds. Or it might even hint at more exotic phenomena, like the first, incredibly distant galaxies to ever form, whose light has been stretched into the infrared by the expansion of the universe. The delicate task of balancing this cosmic energy budget, of ensuring the X-ray whisper and the infrared hum tell the same story, forces us to refine our models of black hole growth and galactic evolution. Any imbalance is not a failure, but a clue, a signpost pointing toward a piece of the cosmic puzzle we have not yet slotted into place. What hidden chapter of galactic history is written in the subtle mismatch between the universe's high-energy static and its pervasive warmth? While the hidden black holes provide a steady, muffled roar, the cosmos is also punctuated by moments of sudden, catastrophic brilliance. A star wandering too close to a supermassive black hole can be caught in an inescapable gravitational grip. The tidal forces are so immense that they stretch and shred the star into a long, thin stream of gas, a process known as a tidal disruption event. In the final, violent moments, as this stellar debris plummets toward the event horizon, it is heated to incredible temperatures, unleashing a blinding flash of X-rays that can briefly outshine an entire galaxy. These cataclysms are cosmic flashbulbs, illuminating the darkness for a few brief months before fading back into obscurity. The mystery they present is one of scale and frequency. Across the vast expanse of the observable universe, with its trillions of galaxies each hosting a central black hole, how often does this stellar destruction occur? If these brilliant flares are common enough, their collective, fleeting light, integrated over billions of years and across all of space, could weave a persistent thread into the fabric of the X-ray background. It would be the combined afterglow of countless stellar murders, a faint but permanent echo of ancient violence. Calculating this contribution is a monumental challenge, precisely because these events are so transient. A hidden, feeding black hole might shine for millions of years, steadily adding its voice to the cosmic static. A tidal disruption event, by contrast, is a single, brilliant shout that vanishes almost as quickly as it appears. To understand their true impact, we need to know not just how bright they are, but how often they happen in a given volume of space over cosmic time. This is the TD rate, a number that is incredibly difficult to pin down. Our telescopes can only monitor a tiny fraction of the sky at any one moment, and we are likely missing the vast majority of these flares, especially the faintest or most short-lived ones in distant galaxies. Are they rare, happening only once every 10,000 years in a typical galaxy, or could they be far more frequent? the answer would tell us if the unresolved X-ray background contains a subtle, shimmering component from the death cries of stars, a high-energy memorial to the countless suns that met their end in the dark grasp of a giant. Perhaps the most thrilling possibility is that the universe's static hum is not just unsolved, but unsolvable with our current understanding of physics. The stubborn portion of the X-ray background that resists all conventional explanations could be the first faint signal of a new cosmic reality, a whisper from beyond the standard model of particle physics. We have already explored the tantalizing idea of dark matter decay, but that is only one of several revolutionary doors that the X-ray background could unlock. Consider the enigmatic possibility of primordial black holes. These are not the black holes formed from dying stars, but hypothetical relics from the universe's very first moments, potentially spanning a vast range of masses. Some theories suggest the cosmos could be swarming with countless asteroid-mass primordial black holes, far too small and dark to see directly. Yet, if they exist, they might not be completely stable. Through a process known as Hawking radiation, these tiny black holes could slowly evaporate, ending their lives in a final, faint burst of X-rays. The combined death rattle of an immense number of these ancient relics could contribute a subtle, diffuse glow to the background, a fossil signal from the dawn of time itself. Another profound candidate comes from the search for actions. These are hypothetical, ultralight particles that were first proposed to solve a deep mystery in particle physics concerning the strong nuclear force. While they have never been detected, they are a leading dark matter candidate. Intriguingly, under the right conditions, actions or similar action-like particles could convert into photons, including X-rays, in the presence of strong magnetic fields. Where in the universe do we find the most powerful magnetic fields? Often, in the same places we find intense X-ray sources, like the turbulent environments of galaxy clusters. It is conceivable that a portion of the X-ray background we attribute to hot gas or hidden black holes is actually the product of these ghostly particles transforming into light as they pass through cosmic magnetic labyrinths. Of course, these ideas are speculative, the long shots of cosmology. The scientific community rightly demands extraordinary evidence for such extraordinary claims, and none has yet been found. But the very existence of an unresolved X-ray background is what keeps these possibilities alive. It is the blank space on the map that invites us to dream, a persistent anomaly that refuses to be neatly filed away. This unresolved glow is the universe's way of telling us that our inventory of its contents and forces is still incomplete. It is a standing invitation to a deeper exploration, a challenge to our fundamental models. What if, hidden within this universal static, is not just another class of astronomical object, but a fundamental key to the laws of physics themselves? The search for an answer is not just about cataloging cosmic objects, but about testing the very boundaries of our understanding. Even the most advanced X-ray telescopes carry their own unique set of mysteries into space. The instruments we build to measure the faint cosmic static are not perfect windows. They are complex machines with their own personalities and subtle biases. Every detector, every mirror has a specific response to different energies of X-ray light. A photon with one energy might be counted with 90% efficiency, while another, slightly different photon might be missed entirely or recorded in a different energy bin. This means the raw data we receive is not a pure image of the sky, but a filtered one, subtly distorted by the very tools we use to see. Calibrating these instruments is a painstaking, never-ending process of cosmic forensics, requiring a deep understanding of how every component behaves in the harsh environment of space. We must observe known, standard candles in the X-ray sky, objects with well-understood spectra, to map out the telescope's precise response. Only then can we begin to reverse engineer the distortions and reconstruct the true nature of the background radiation. A tiny miscalibration, a 1% error in our understanding of the mirror's reflectivity, could create a false bump or dip in the final spectrum, sending astronomers on a wild goose chase for a new particle or a hidden source that does not actually exist. The first and most fundamental mystery is therefore knowing if we are seeing the universe clearly, or if we are merely seeing the reflection of our own technology. Compounding this instrumental puzzle is a far more local form of interference. Our solar system is not a perfect vacuum. It is filled with a constant stream of particles flowing from the sun, the solar wind. When these charged particles, like protons and alpha particles, encounter neutral gas drifting through our cosmic neighborhood, such as the sparse atoms of the local hot bubble or even the tenuous outer atmosphere of a comet, a strange and beautiful process occurs. The solar wind particles can steal electrons from these neutral atoms. This electron capture causes the now recombined ion to drop into a lower energy state, releasing the excess energy as an X-ray photon. This phenomenon, known as solar wind charge exchange, creates a faint, ever-shifting fog of X-rays that glows throughout our entire solar system. From our vantage point, this local emission is superimposed directly on top of the distant cosmological background. It is the ultimate cosmic practical joke, a signal generated in our own backyard that perfectly mimics the ancient static we are trying to study. Distinguishing between the two is a nightmare. The solar wind is dynamic, changing in intensity with the sun's activity cycle, and its charge exchange emission shifts and flickers across the sky. Astronomers must create complex, time-dependent models of this solar fog, predicting its brightness and distribution based on solar activity and the density of local neutral gas, and then carefully subtract it from their data. Any error in this subtraction leaves behind a ghost in the machine, a local phantom that could be mistaken for a discovery about the warm, hot intergalactic medium or a new class of diffuse source. The quest to understand the cosmic X-ray background is thus a dual struggle, a battle against both the limitations of our own machinery and the deceptive glow of our immediate environment. To hear the faint whisper of the cosmos, we must first learn to silence the hum of our own celestial household. The ultimate key to these mysteries may already be forged, waiting in clean rooms for their ride into the heavens. A new generation of X-ray observatories is on the drawing board, instruments so powerful they will transform our murky cosmic static into a sky ablaze with individual points of light. The European Space Agency's Athena mission, the Advanced Telescope for High-Energy Astrophysics, is one such giant. Its revolutionary X-ray mirror will have a collecting area more than 100 times larger than current telescopes, allowing it to gather faint photons with unprecedented speed and clarity. With Athena, a deep field observation that currently takes weeks will be completed in mere hours, surveying vast swaths of the sky with a sensitivity we can only dream of today. This is not just an incremental improvement, it is a quantum leap. Athena will resolve a huge portion of the remaining hard X-ray background into individual sources, finally pulling thousands of the most heavily obscured black holes out of the shadows. But its power does not stop there. Athena's incredible spectral resolution will act like a cosmic prism, splitting the X-ray light into such fine detail that we can read its composition like a precise chemical recipe. It will hunt for the faint absorption lines from the warm, hot intergalactic medium with definitive clarity, potentially solving the missing baryon problem once and for all. It will study the 3.5 kilo electron volt line with such precision that we will know, beyond a reasonable doubt, whether it is a sign of dark matter decay or a complex atomic process. Across the Atlantic, NASA, a Lynx concept envisions an observatory with unmatched vision. Its goal is to achieve sub-arcsecond angular resolution in the X-ray band, a sharpness that would reveal the faint, whisper-thin glow of hot gas in the distant, faint galaxy groups that have so far been only theoretical ghosts. Lynx would see the cosmic web itself, mapping the faint X-ray emission from the filaments that connect clusters of galaxies, directly imaging the hidden architecture of the universe. These future telescopes will not just add more data, they will change the very questions we can ask. They will watch the evolution of black holes and galaxies unfold across cosmic time in exquisite detail, tracing the flow of hot gas into and out of galaxies to understand the great cosmic cycle of matter. The faint anisotropies in the background will become a rich statistical landscape to be explored, not just a faint whisper to be barely heard. The persistent static that has challenged astronomers for decades will, piece by piece, be transformed into a symphony of distinct voices, each telling its own story of violence, growth, and hidden power. The hope they represent is not just for more answers, but for a fundamental shift in our perception, a moment when the universe's greatest high-energy secrets are finally brought into the light. The faint X-ray static we detect is a historical record written in light, but light is only one messenger from the cosmos. We are now entering an era where we can read the universe's story through multiple senses, a revolution known as multi-messenger astronomy. This new approach combines the traditional study of light with the detection of gravitational waves, the ripples in space-time from colossal collisions, and neutrinos, the ghostly particles that pass through almost everything. This powerful synergy offers a completely new way to crack the mysteries of the X-ray background. Imagine detecting the gravitational wave chirp from two neutron stars merging in a distant galaxy. That signal tells you an event has happened and roughly where to look. Astronomers then swing every telescope they have toward that patch of sky, searching for the aftermath. If that merger produces a short, powerful burst of gamma rays, it is often followed by a lingering afterglow, a fading fireball that can shine brightly in X-rays for hours or days. By catching this X-ray counterpart, we learn something profound about the physics of the merger itself, about the jets of material it launches and the heavy elements it forges. But beyond understanding a single event, this process helps us calibrate the entire cosmic population of these compact object mergers. Every time we successfully match a gravitational wave to an X-ray flash, we are essentially tagging one of these violent systems in the wild. We learn how common they are, how much energy they release in X-rays, and how they evolve over cosmic time. This is crucial for modeling their collective, integrated contribution to the ancient X-ray glow we see today. The unresolved background is the sum of countless such events across the history of the universe. By using gravitational waves to take a modern census of these mergers, we can run the clock backwards and make a much better estimate of how many of them were happening 10 billion years ago, and how loudly their combined X-ray whispers should echo through the cosmic static. The same logic applies to neutrinos. A single high-energy neutrino detected by observatories like IceCube at the South Pole can act as a celestial arrow pointing back to its source. When such a neutrino is traced to a flaring active galactic nucleus, it confirms that these monstrous black holes are powerful particle accelerators. This, in turn, helps us understand the complete energy budget of these systems, revealing how much of their power is channeled into light, how much into particles, and how all of it combines to shape the pervasive high-energy fog. Multi-messenger astronomy transforms the X-ray background from a static, monolithic puzzle into a dynamic, living entity. It allows us to connect the faint, ancient light we cannot resolve with the loud, modern signals we can, using the present to decode the past. Each new gravitational wave or neutrino alert is not just about one event. It is a potential key to understanding the collective murmur of billions, a single, clear voice helping us interpret the universe's oldest choir. This final, lingering static forces us to confront a profound possibility. What if a portion of the cosmic X-ray background is destined to remain forever unresolved, a permanent fog in our map of the universe? This is not a failure of science, but a fundamental statement about the nature of reality and our place within it. The existence of an unresolved glow could represent a hard limit to our powers of observation, a cosmic horizon beyond which we simply cannot see. Our telescopes, no matter how advanced, might one day reach a point where they cannot distinguish individual sources, not because the instruments are flawed, but because the universe itself is structured this way. The light from countless trillions of faint objects, like distant dwarf galaxies or the faintest stellar cinders, could be so hopelessly blended by sheer distance that their combined murmur becomes an inseparable part of the cosmic canvas. It would be a universe of unimaginable population, where for every star and galaxy we see, there exist countless more, forever hidden in the statistical noise. Alternatively, the answer might be even more radical. The glow could be truly diffuse, not from point sources at all, but from processes woven into the fabric of spacetime itself, or from the collective decay of particles so exotic we have not yet given them a name. This unresolved background is more than a scientific problem, it is a philosophical mirror. It reflects back to us the limits of our current knowledge and the boundless potential for discovery that still lies ahead. It reminds us that the universe is under no obligation to be completely knowable to us. Some secrets might be built into the very nature of existence, permanent mysteries that humble our quest for a final answer. Yet, this is not a reason for despair, but for awe. The faint, persistent hiss is a constant companion to our exploration, a whisper that there will always be more to learn, more to question, and more to wonder about. It ensures that the cosmos will never lose its capacity to surprise us, inviting every new generation to listen a little closer to the static and hear the echoes of the unknown. This faint, universal static is not merely empty noise, but a living archive of cosmic violence and hidden growth. We have journeyed through 25 profound mysteries, from the feeding frenzies of invisible black holes and the ghostly web of missing matter to the tantalizing spectral line that could be the dying breath of dark matter itself. Each unresolved whisper in this high-energy fog points to a deeper layer of reality, a story we are only just beginning to read. The cosmic X-ray background is the universe's grand narrative, written not in ink, but in the searing light of its most powerful and secret events. The journey does not end here. Stay curious. Follow the launch of revolutionary new eyes on the cosmos, like the Athena and Lynx observatories, as they prepare to pull these ghosts into the light. The greatest discoveries are still ahead of us, waiting in the static. We would love to hear which of these cosmic mysteries captivates you the most. Share your favorite enigma in the comments below, and thank you for joining this exploration into the high-energy heart of the universe.